Hello, my name is Muhammad Ayaz Azim and I'm here to present COVID-19 chest X-ray image classification using deep learning. COVID-19 detection challenge. The COVID-19 has spread globally and caused unprecedented damages worldwide. Technology, in particular AI, can play a vital role in helping fight against this pandemic. In addition, lessons learned can be helpful in fighting and preventing future pandemics. The challenge aims to develop a multi-class classification algorithm capable of detecting and classifying COVID-19, normal and pneumonia in chest X-ray. The evaluation criteria was based on accuracy, sensitivity, and specificity in this order. Data distribution. The dataset contains three image classes: COVID-19, pneumonia, and normal. Training dataset contains 17,958 CXR images. Validation dataset contains 3432 CXR images, and test dataset that was released on 1st October 2021 consisted of 1200 CXR images. A sample image from training dataset is shown here. Methodology. Transfer learning technique is used by loading the weights of the pre-trained ImageNet. Adam Optimizer is used as it is fast and converges rapidly. Two loss functions are used: pullback, Libler divergence, and categorical cross entropy. A callback function is employed that permits us to identify the performance parameters to monitor the start and conclude the training process. Best model is selected using the early stopping callback function. Best model is then executed on training dataset, validation dataset, and test dataset. Digging a little deeper to explain the architect of the base model in our experimentation, data is read and 0, 1, and 2 are assigned to COVID, normal, and pneumonia respectively as per the instruction. Resizing of images is done and 256 of 256 multiplied by 256 uh, in order to achieve the statistical results. The images of the input classes are augmented using an API Keras augmenter. Image rotation is performed with a rotation factor of 15. All images, original and augmented, are passed to image data generator class in Keras to carry out pre-processing operations such as augmentation. 4 deep learning models are used and employed in our experimentation. A brief description of these 4 deep learning models is on the next slide. 5 layers are added to generate the base model. The base model is then compiled. A callback function is employed that permits us to identify the performance measures to monitor the trigger, and once triggered, it will conclude the training process. A specific callback function with the name reduced learning rate on Plato is used in our experiment with a patience factor of 30 and a learning reduction rate of 0.001. The early stopping callback function will conclude the training process. But the model at the end of this training phase may not be the model with the best performance on the validation dataset. To overcome this issue, model checkpointing is used to obtain the best model that shows optimal results as per our parameters. Model.fit is obtained. Once we have loaded the best model, it is then applied to train dataset, validation dataset, and test dataset. The 4 deep learning models implemented in our experimentation are VGG16. VGG16 is a convolutional neural network architect with very small convolutional filter with a size of 3 by 3 and a stride of 1, designed to achieve higher accuracy in large-scale image recognition application. The implementation of VGG having the depth of 16 fully connected layers of convolutional and max pooling in the base model. The model achieves 92.7% accuracy in ImageNet, which is basically a dataset of 14 million images belonging to 1000 classes. It was one of the top performing models submitted in ImageNet challenges in 2014. Two loss functions are used: Kullback Libler divergence and categorical cross entropy, where KLD finds the Kullback Libler divergence finds the difference between the two distributions. The second deep learning model implemented is Inception V3. Inception V3 CNN aims to improve utilization of computing resources inside the network by increasing the depth and width of the network while keeping computation operations constant. The Inception V3 was designed to permit deeper networks while also keeping the number of parameters in check. It was built to be a network with under 25 million parameters in comparison with AlexNet that had 60 million parameters. The designers of this network coined the term Inception module to describe an optimized network structure with skip connections that is used as a building block. The third deep learning model used in our experiments is ResNet 50. ResNet CNN was developed as a means of avoiding the vanishing gradient problem inherent in deep learning neural networks by implementing a system of skipped connections between layers known as residual learning. The architecture results in a network that is more efficient to train, allowing for deeper networks to be designed that positively impacts the model accuracy. ResNet 50 is such a network with 50 layers of implementing residual learning. The four deep learning model implied in our system is DesNet 121. DesNet 121 CNN uses shorter connections between layers in order to allow more accurate and efficient training on very deep networks. Model stats for training dataset. The five variations of the four deep learning models uh, mm, are shown here with where epochs represents the number of epochs to obtain the best model. VGG with KLD means with Kullback-Leibler divergence and this one is categorical cross entropy loss function. Uh, uh, that these five variations of the four deep learning models were applied on 17,958 training dataset CXR images, and we have found out that uh, VGG16 with Kullback-Leibler divergence loss function achieved accuracy of 96.58%. The same five variations of the four deep learning models were applied on the validation 3432 CXR images, and we have found that VGG16 with categorical cross entropy loss function uh, outperformed other model and achieved the accuracy of 95.54%. The five variations of the four deep learning models were applied on the test dataset, uh, and we have found that VGG16 with the categorical cross entropy loss function was able to achieve the accuracy of 94%, sensitivity of 94%, and specificity of 94.20%. So, to sum it up, in this study, a multi-class deep learning model was designed and evaluated for detecting and classifying COVID-19 normal and pneumonia from chest X-ray images. The VGG16 model with 16 batch size, pre-processing image size of 256 by 256, categorical cross entropy loss function detects and classifies COVID-19 normal and pneumonia with 94% accuracy and ranks 14th place on leaderboard. Ongoing work attempts to enhance the performance of the proposed model by using other deep learning techniques such as GANs in both detection and classification. At the very end, we'd like to acknowledge the supports and computational resources provided by CSC. We'll also like to thank University of Johannesburg for organizing such a wonderful conference. Thank you.